Welcome back. We will be looking at unconstrained optimization now, and we're going to begin with an important theorem. This is known as the extreme value theorem. So this is what it says. If D is a closed and bounded subset of the 2 space, and if the function f of xy is continuous on D, then f attains an absolute maximum f of AB and an absolute minimum f of CD on D. That is, f of AB is larger than f of xy for any xy in D, and f of CD is less than f of xy for any xy in D. So basically we are saying that if the function f is continuous on a closed and bounded subset D of R2, then there is a point AB in D and a point CD in D such that f of AB is the largest value of f on D and f of CD is the least value of f in D. Okay, so this is just saying that on such a domain that f will always attain extrema. To find the so if I have a closed and bounded set D, then how do I find the maximum and minimum of f on D? Well, either max and mean, I'm just going to call them extrema. Either the extrema of f occur on the boundary of D, or they occur inside of D. Now, so if an extremum occurs inside of D at a point interior to D, then at that point f must have a local max or a min, and because of that we know then at a local max or a min we have a critical point. So that means the extrema of f either occur on the boundary of the closed and bounded set D, or they occur at points interior to D where we have critical points of f. So to find the max and min of f on D, the first step we should be doing then is find the critical points of f which are interior to D, and then find the extrema of f on the boundary of D, and then the absolute maximum would be the largest of the values obtained in part 1 and 2, and absolute minimum would be the least of the values obtained in part 1 and 2. So again, we have, if we have a subset D of R2 where D has a boundary, then we are saying that the max, if f is continuous on D, then the maximum or the minimum of f occurs either on the boundary or at a point interior to D where we have a critical point. So we need to find critical points inside of D and evaluate f at the critical points, and then we find the max and min of f on the boundary of D, and then we compare them to find the absolute max and min. So let me illustrate that on this example. Let's say that we want to find the absolute maximum and minimum values of f, which is x squared minus 2xy plus 2y on the set D, where D is the set of all points xy such that x is between 0 and 3 and y is between 0 and 2. So what is that D? Well, D is this rectangular region in the xy plane, and it is a closed set because all the boundary points are included, and it is bounded because you can enclose it in a big circle centered at the origin. So this is so f is continuous on this, so f has a maximum and a minimum on D. So now we try to find them. Here I have the graph of this function right above the region D. And what we're going to show is that the maximum of this function occurs at the point 3, 0, and then we'll also see the minimum. So again, the first step is to find the critical points of f that are inside of D. So the critical points of f, so that means I have to solve the equations fx equal to 0, fy equal to 0 simultaneously. And what is fx in this case? Well, the function that we have here, let me copy that. So the function that we have here is this. Okay, so this is the function. So what is fx? Fx would be 2x minus 2y. And what is fy? Fy is going to be negative 2x plus 2. Okay, so this is the system of equation we need to solve. Now from the second equation, clearly x is negative, x is 1. And from this, once we have x equal to 1, then I can plug that in the first equation, and then I see that y has to be 1 as well. So we see that 1, 1 is the only critical point we are getting. And the question is, does 1, 1 belong to the region D? Well, the answer is yes, because it includes all the points where x is between 0 and 3, y is between 0 and 2. So 1, 1 is somewhere there. So 1, 1 is an interior point of D. So we have only one critical point inside of D. And the value of the function at 1, 1, well, here is f of xy. So what is f of 1, 1? F of 1, 1 would be 1 squared minus 2, 1, 1 plus 2, 1. And if we calculate that, we get 1. So we have found the value of the function at the only critical point that it has inside of D. All right, so the next step is to find the maximum and minimum of f on the boundary of D. Now the boundary has 4 sides here. So I'm labeling them L1, L2, L3, L4, and we need to find the max and min of f on each of these sides. Now these are the pictures that I have taken from the text, the Stewart's text on calculus. So notice that on the line L1, y is always 0. So if I look at, so then on L1, what's the value of f? Well, f of xy on L1, so y is always 0 on L1. So we get f of x0, which is equal to x squared, because the function that we have here is this. So when y is 0, we get x squared only. So the function is equal to x squared when y is 0. I'm calling that g of x, and so x is between 0 and 3 here on this line L1. So x squared is clearly an increasing function from 0 to 3. So the maximum of this function occurs at 3 and the minimum occurs at 0. And we see that the minimum would be then f of 0, 0, because remember y is 0 here. So f of 0, 0 would be the minimum, which is 0. And the maximum would be at 3, so f of 3, 0, that's 9. So those are the max and min on line L1. Now let's go to line L2. Let me see if I can bring back the function formula here so that I don't have to go back. And just so I know. Okay, so now on L2, notice that on L2 x is always 3. So the function f of xy on L2 would be f of 3y and f of 3y. So I'm replacing x by 3, so I get 9 minus 6y plus 2y. So minus 6y plus 2y would be minus 4y. So on L2 then, f of xy is the same as 9 minus 4y, which is what I'm calling g2 of y, and y is between 0 and 2. So now if you look at this function, this is a linear function with negative slope, so that means it's decreasing function. So because it's decreasing, then the maximum would occur when y is 0 and the minimum would occur when y is 2. So the minimum is f of 3, 2, so which would be when y is 2 you get 1, and the maximum would be f of 3, 0, which is 9. So when y is 0 you get 9. So that's the maximum. So on L2 the maximum occurs at 3, 0. On L1 the maximum occurs at 3, 0 as well. Now we move to L2. Let me move it up here. So now we move to L3. So on L3, notice that y is always 2. So f of xy would reduce to f of x2, which I'm calling g3 of x, and x is between 0 and 3. And when we replace y by 2 here, so you get negative 4x plus 4 here. So you get x squared minus 4x plus 4. Okay, so we look at this function and then we want to find the max and min when x is between 0 and 3. Now you can factor this out and write that as x minus 2 squared. And so okay, so this is a parabola, right? This is a parabola that is this is a yeah, you can look at the graph of that and see where the minimum would be at the vertex. But let me say it this way. So you have x minus 2 squared. So in order to maximize this, you have to make sure that x minus 2 is as big as possible in absolute value. So notice that you want x to be as farther away from 2 as possible. Well, that would be at 0, because 0, when x is between 0 and 3, among these values of x, 0 is farthest away from 2. So the maximum would be when x is 0. So and so when x is 0, we get f of 0, 2, which is 4. And the minimum would be, well, you want to make this, you want the distance from x to 0, 2 as small as possible. Well, if you pick x to be 2 here, then you get 0. So that would be the minimum. So when x is 2, f of 2, 2, that's the minimum on L3. Now, I could have done it differently. So this is just a function of a single variable. And so we can use what we learned in Calc 1, which is how to find the max min here of this function. So I could have found the critical point of this function, that is the point where the derivative is 0. So we can find the critical points of the function and then evaluate this function at its critical points and at the end points of this interval, and then compare them and find the max and min. So that's another way of going about it. Now, when this function is more complicated, that's what you have to do. And then on L4, notice that let me bring down the function here. So on L4, notice that x is always 0, so the function f of xy reduces to f of 0y, and f of 0y would be simply 2y. That's what I'm calling g4 of y. As a function of y, it is an increasing function, and y is between 0 and 2, so the maximum would be when y is 2, minimum would be when y is 0. So the minimum would be f of 0, 0, which is f of 0, 0, which is 0, and the maximum would be f of 0, 2, which is 4. So now we compare. So recall that we got the value f of 1, 1 is 1 at the critical point, and then we got the min and max 9, and then we got min 1 and max 9. We got 0 and 4, 0 and 4, and we got here 0 and 4 again. So we see that 0 is the least value, and 0 occurs at 0, 0 and 2, 2, and the maximum is 9, and that occurs at 3, 0. So after we compare them, this is the conclusion we make, that the absolute value of f on d is 9, which occurs at the point 3, 0, and the minimum value of f on d is 0, which occurs at 2 points, f of 0, 0 and f of 2, 2. Okay, so that's the example that should illustrate how to find the maximum and minimum of a function on a closed and maximum minimum of a continuous function on a closed and bounded subset of the 2 space. Okay, so I'll stop the video here, and I will see you in the next video.